All right, we got one more video before we wrap up this semester from section 10.3 of Susanna App's Discrete Mathematics Brief Addiction. We're going to talk about trees in this section. Tree is a special kind of graph. Remember, we've been looking at graphs for some time now. These are sort of abstract representation of networks where the vertices of the graph, which are represented by points on the plane or on the page, represent sort of the nodes in the network, whether those are cities or atoms in a molecule, etc. And the edges or the line segments connecting the vertices of a graph are abstract representations of the connections between the nodes in the network that you're looking at. So those could be hyperlinks between websites or highways between cities, molecular bonds between atoms in a molecule, and so forth. So trees are a very special kind of graph. They are connected acyclic graphs, and we'll get into that a little bit more in a moment. But what that means, roughly speaking, is they're all one piece. We talked about connectedness in the last couple of sections. The graph is one piece. Every vertex can be reached from any other vertex by following some walk or path. And they are acyclic, which means they lack closed circuits. A cycle is a simple closed walk, a simple closed path, more precisely, where you begin at one vertex and you follow some course throughout the graph, and you end up back where you started without repeating any vertices except for the first and the last one. So if you are connected, all one piece, and acyclic, have no cycles where you begin and end at the same vertex without repeating edges, you are a tree. So let me just write that definition down, draw a couple of pictures, and we'll talk about some examples of trees, and we'll just prove a couple of basic facts about them to wrap up the semester. So again, a tree, by definition, a tree is a connected, acyclic graph. Connected we've talked about before, meaning it's all one piece. From any vertex you can get to any other by following some walk or path. And again, acyclic just means there are no circuits. That is, there's no way to get from one vertex back to itself by following some path without repeating edges or vertices. So it's really easy to tell graphically if a graph is a tree. You look to see if it's all one piece, and you look to see that there's no cycle or circuit in it. So trees could be either directed or undirected. Sometimes it's helpful to be able to put some direction, for instance, on the edges of a tree to indicate some parent-child relationship. Section 10.4, which we will not talk about this semester, section 10.4 of your textbook talks about what it would look like to have a directed tree where you have a parent node which gives rise to child nodes and grandchildren and so forth, almost like generations. But we can also draw trees without any direction to them. That's undirected graphs. So there is no special parent node or root node for the tree. We can just begin anywhere we want to. And this would be an example of a tree, and you can see why it might be called a tree. The branches of a tree grow outward and they don't loop back on themselves. This is indeed connected. It's all one piece, and it's acyclic. We don't see anything like this in it. We can't start at one vertex, follow some circuitous path, literally some circuitous path, and get back to that initial vertex without repeating edges. So if we wanted to, for instance, go to that vertex, come back, we would have to repeat various edges. We'd have to repeat all the edges in the path that we followed in the first place. So a tree has a connected acyclic graph. A forest, by the way, and yes, this is a technical term, is a non-empty collection of trees. So if you have a bunch of trees and you put them together on the page together, that's a forest. The only difference is it's no longer connected necessarily. However, there's nothing in the definition of a forest that says you can't have just a single tree. It says you have to have at least one, a non-empty set. So there's got to be at least one tree there. But a single tree is a forest, interestingly enough. So if anytime you have one or more trees kind of bundled together, that's what we call a forest. And yes, again, that is a technical term. Graph theory is one of the most fun branches of math because you get some really interesting technical terms like firecracker, banana tree, lobster, caterpillar, these are all technical terms in graph theory. All right, so again, the only difference between a tree and a forest is the connectedness, because if you had a forest, think about having this tree, I'll get rid of this non-existent path right there, this tree, and maybe throw a couple more trees in there, and you consider them all together. The only difference between this tree, this collection, this forest, and a tree is the connectedness. There's still no cycles, and you can see that if we added a couple of edges strategically to connect the various trees in this forest, we would in fact have another tree. In fact, we're going to talk about that in a little while here when we look at the relationship between the number of vertices in a tree and the number of edges in a tree. Before we go into that though, just a couple of quick examples. We've already seen a tree. We didn't think of it as a tree. Maybe we did actually. We talked about it. We called it a possibility tree or a probability tree. So examples, we had a possibility or a probability tree. Probability. Can't spell today. And this was back in or chapter 9 rather, when we were looking at probabilities. We used a probability or a possibility tree to keep track of the number of ways of completing some multi-step process, and we used the multiplication rule. Remember, this was section 9.2, I want to say. I think it was section 9.2, where we talked about using the multiplication rule to determine the likelihood or the probability of a multi-stage event happening by looking at the different branching possibilities as the process went on. You've probably also seen in a couple of different branches of computer science in formal languages or programming languages, you may have seen parse trees or syntactic derivation trees, where you can parse the structure of a command given to, or a line of code given to a program by looking at the various elements of that command or that sequence of commands even, the various roles they play in the programming language, almost like diagramming a sentence. If you think about, if you've ever diagrammed a sentence in a natural human language, it's the same kind of idea. You're doing a syntactic analysis or syntactic derivation of the various components of the sentence, whether you've got a subject or a verb and so forth. And another example I want to include here is various data structures. So if you've taken a data structures class, you have things like binary trees, red-black trees, AVL trees, are all examples of data structures where you can store information in some way that makes it easy to access, easy to search, etc., with various criteria. These are all different flavors of search trees. So you store the information in such a fashion that a particular kind of search can be done on it quite effectively and quite efficiently. So trees come up an awful lot in computer science applications and in combinatorial applications that frequently come up in computer science. All right, so trees, forests, some examples. Let's look at a couple of the characteristics of these trees. And I want to take as our starting point here just some observations from these trees that we have here, maybe even some simpler trees. Even that one right there, that's a tree. Just a single vertex is a tree, right? It's connected, it's acyclic. By the way, notice that trees have to be simple graphs, because as soon as you have a self-loop or parallel edges, you violate the acyclicity of the tree. So you can't have any loops or multiple edges between vertices, otherwise you're by definition not a tree, so we're always simple. Let's look and see, for each of these examples, count the number of vertices and count the number of edges. So just visually, these are all trees that connected in acyclic. If we look at the number of vertices and the number of edges in this tree, just to start with here, we've got 2 vertices and a single edge. We look at this one here. how many vertices, how many edges do we have? We have 1, 2, 3 vertices, 1, 2 edges. Down here, this very simple example, we have 1 vertex and 0 edges. You're starting to see a pattern. Now these are a little more complicated. Pause the video if you haven't yet seen the pattern. And when you're ready, you can unpause the video and and verify. Indeed, the number of vertices in each of these cases appears to be 1 more than the number of edges. So if we count the number of vertices in this guy, it looks like we have 7. Without even counting the edges, we should determine that the number of edges is 6. 1, 2, 3, 4, 5, 6. We were right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices in this case, which means we should have 10 edges. And I don't know why I keep pausing like that. Just to mimic the pause of the video. So we should always have 1 fewer edge than we have vertices, and that turns out to be the case. And we're going to prove a lemma. We're going to prove a lemma before we prove what I just said as a theorem. So the claim or the theorem that we're going to make is that if T is a tree, then let me rephrase that. If T is a tree with n vertices, then T has, what did we just say, n minus 1 edges. And to prove this, which we're going to do by inducting on the number of vertices in the tree, we're going to use a lemma. So we need the following lemma. If T is a tree with at least 2 vertices, then it has at least 2 leaves. And I didn't say what a leaf is, but it's pretty obvious from the picture of a tree what a leaf must be. I'm just going to draw a sample tree here. So let's say this is a tree over here. Again, thinking of the tree as growing outward from a particular point, doesn't matter which one, we're not distinguishing any point as special, but think of it as growing outward. The extremal points, the points where we've gone the furthest out from any central point, are the leaves. And that would be these vertices dangling off on their own. Technically, these are vertices of degree 1. So a leaf in a tree is just a vertex of degree 1. And in this case here, let me use, here we go. In this case we have 1, 2, 3, 4, 5, 6, 7, 8 vertices. So I've circled the vertices in red here. On the other hand, we've got 1, 2, 3, 4, 5 other vertices that I've circled in blue that I'll call branch vertices. So if you're looking at a tree, the 2 types of vertices you could have are the leaves, the extremal ones that are out on the ends, the degree 1 vertices, or the branch vertices. And you call them branch vertices because those are places where you branch in multiple directions, but branching requires you have degree at least 2 because you need at least 2 options to leave that vertex. So leaves and branch vertices. The claim we're making here is that if you have a tree, then it has at least 2 vertices that are leaves. So as long as you have at least 2 vertices total. Obviously, if you only have 1 vertex, there's no way you could possibly have two leaves in it. So the proof we're going to do, I'm going to do this somewhat informally, but we'll be a little careful here. You can prove this by induction, by the way. There are ways to prove this by induction, but we're going to do it directly. So proof of the lemma, to be clear, we're going to prove the lemma first. Let T be a tree with at least 2 vertices. And what we're going to do is kind of a proof by contradiction. What we're going to do is construct a path that's as long as possible and show that the 2 endpoints of that path have to be leaves. Take a longest possible path. Let's call it P. in T, and let U and V be its endpoints. So I'm just going to draw kind of a picture here. U, V, this whole thing is T, and here is the path that goes from U to V inside of T. That's the longest possible path we can find. Now remember what a path is. A path is a, what do I want to say? A path is a walk. It's a succession of vertices alternating with edges that goes from one vertex to another without repeating any vertices, and therefore not repeating any edges. Remember that a walk allows you to repeat vertices and edges, but a path says you can't repeat any vertices, and therefore you can't repeat any edges, because if you repeated an edge, you'd also be repeating its endpoints. Okay, so we go from U to V without repeating any edges. The claim is that this is going to be, rather that U and V are going to be leaves of the tree. So let's say that it wasn't the case. Let's say maybe that we had some W that was adjacent to U that was not the first vertex on this path. We don't really need a name for that guy. But let's say W is a vertex that's adjacent to U that is not on the path P going from U to V. Well, if, let's say, what do I want to say here? So, yeah, if there were such a W, there are a couple of possibilities. There is no way, like I said, if we're assuming that W is not equal to that vertex there on the path, I guess there's only one possibility, I lied. If W is not the vertex, the first vertex on the way back to V, then what can we do with W as regards, what was I going to say here? What can we do with W as regards the path P? Because W is not that vertex. We assumed it wasn't. What we could do is we could follow the path V from V to U and then add W on the end. If there were a vertex W adjacent to U and not on P, adding W to the end of P would lengthen, that is not how you spell would lengthen P, making a longer path. And this can't be. This is a contradiction. Remember that symbol we had a while ago, the lightning bolt for a contradiction. Because we assumed P was as long as possible. So there's absolutely no way we could have had this W here that wasn't already on the path P, because otherwise we would have gotten a longer path. So that means that U, thus there is no such W. And the degree of U must equal 1. Because what this is saying is the only possible way we could get out of U is not through some guy that's not on the path. That means the only vertex that's adjacent to U is that guy on the path. Otherwise, we could have lengthened the path, made it longer. So the degree of U is V, and analogously, the degree of V is equal to 1 as well. And that's actually the end of our proof, because that's the definition of a leaf. U and V both have degree 1, and therefore they are leaves. And those are the leaves that we wanted to show existed. Notice I said analogously, I didn't go through the proof. It's exactly the same proof because we could have made the same supposition about some W adjacent to V as well. It's exactly the same proof. We don't have to go over that again. So, what we've proven so far is that if T is a tree with at least 2 vertices, we have at least 2 leaves. I claim that's going to help us figure out how to prove the theorem. This is called a lemma. Remember, we've talked a little bit about lemmas. Lemmas are like theorems. They're mathematical results we can prove. prove, they're just not as interesting as theorems, not as interesting in their own right. They're only used as stepping stones to proving more important results like this theorem here. Let's go ahead and clean up this side, and then we'll prove the theorem. Right. So remember, the theorem says, just as a reminder, if T has n vertices, then it has n minus 1 edges. That was the observation we made on this side before I erased it, looking at all those examples. The proof of this, by the way, it goes two ways. If you have a graph that has n vertices and n minus 1 edges, you know it's a tree. That's a connected graph that has n vertices and n minus 1 edges. So this is an if and only a thing. We're not going to prove that. So proof. By induction on n. Let's take the base case. In fact, we'll do the base cases because we actually need to get to the point where we can use this lemma, which means we need at least 2 vertices. So the base cases are if n equals 1, then T is a single vertex, right? If T has 1 vertex, this is what it looks like, which has n minus 1 equals 0 edges. So it's true. If n equals 2, it's pretty obvious that the only tree on 2 vertices is that one right there, a single edge. So which has 1 edge, and 2 minus 1 equals 1. In other words, it clearly has a single edge, and the formula we're claiming is should give us 1 edge as well, and so the 2 values match up. So our base case is true. For our inductive hypothesis, assume a tree with k vertices for some fixed arbitrary k has k minus 1 edges. By now we've done a whole bunch of induction proofs, so you should have that a sense for what that means. And now for our inductive step. Let T have k plus 1 vertices. And let's assume, we can assume that k plus 1 is at least 3 because we've handled all the other cases. We've handled smaller cases where k plus 1 is at least 3, so k is at least 2 if you take 1 vertex away. All right, in particular, if we know, so let me just draw this. So here's what our T looks like with k plus 1 vertices. By the lemma, T has at least, that is a really, really, really horrible spelling of least, at least 2 leaves. And let's call them U and V. It turns out we really only need one leaf for this to work. So what am I going to do? The reason I want a leaf is because I want to be able to remove it really easily without disrupting the tree too much. Notice that removing U, just one of them, I don't have to remove both, gives a tree, let's call it T prime, with how many leaves? Or sorry, how many vertices? We know that T, this picture I've drawn over here looks like a potato with pins sticking out of it. We know that T itself has k plus 1 vertices. So if I swipe one of those vertices away, rip it off, and make T prime, we have a new tree with k vertices. Now, I claim it's a tree. It's pretty obviously a tree because you can't make cycles by taking a vertex away. So we're still acyclic because T was. And we are also connected because, again, if you're removing a little dangly 1 degree vertex guy, tearing this vertex off doesn't create any new cycles, and it doesn't disconnect the tree. You're still connected. So taking off you makes a new tree with 1 fewer vertex. It's still connected, still acyclic. Aha! And we can apply our inductive hypothesis. So by the inductive hypothesis, T prime has k vertices and therefore k minus 1 edges. So adding back u gives 1 additional edge. We took u off to get a smaller tree to which we applied the inductive hypothesis to get k minus 1 edges. And now we add u back along with its little edge that connects it to give us k edges in T. And that's it. That's the end of our proof. So we're able to prove that a tree with n vertices has n minus 1 edges in it. Now, we don't want to go with that. So a couple quick comments I want to make. Blah, 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 blah. One quick comment I want to make is we can generalize this. In fact, I'm going to ask you in the quiz to generalize it further. I'm going to turn this around, so you might want to pause the video and make sure you understand this. We can generalize this to talk not about trees, but about forests. Let me get the whiteboard cleaner here. So I kind of hinted at what I'm about to say toward the beginning of this lesson when I drew a forest and I kind of connected it up by adding a few edges to make a tree. There's actually a deeper relationship there. If I had 3 forests, and I think that was what I did in the example, if you want to scoot back for a moment and check. If you had 3 forests and you connect them together, zoom in a little bit here, old-fashioned style. 3 forests and you connected them up with edges to form a single tree, you had to add 2 edges. One connecting one forest to the second one, and a second edge connecting the second forest to the third. So, again, if I had a forest with 3 connected components in it, then I had to make a tree, I had to add exactly 2 edges between each of the successive guys in the forest. It doesn't matter how I do this. I could connect different vertices and I'd still get a tree. Or I could even connect the components in the forest in a different order. I could connect these 2 to each other and then those 2. But anyway I connect them by adding a single edge between a successive pair of forests gives me a new tree. So here's the claim I want to make. That sort of generalizes the theorem on the other side that we just proved. If G is a forest, I'm not using the notation T anymore because it's not a tree. If G is a forest with n vertices and 2 connected components, how many edges? How many edges does it have? I actually did this example over here, which is a little more complicated than the question I'm asking here. If I had, say, T1 and T2 are the 2 connected components of the graph G. This whole thing taken together is the graph G. How many edges do I have to have? Well, I know I've got n over here. Maybe I've got n1 and n2, where I know that n is equal to n1 plus n2. Right, I've got n1 vertices over here. I've got n2 vertices over here, and the total number is n. Well, from our theorem on the other side, I know that I'm going to have n1 minus 1 edges over here, and I'm going to have n2 minus 1 edges over here, because the theorem applies to trees and not forests. So this connected component is a tree with n1 vertices and therefore n1 minus 1 edges. This connected component is a tree with n2 vertices and therefore n2 minus 1 edges. And so the number of edges in the total graph G is going to be the number of edges in the first part plus the number of edges in the second part. And I can rearrange. And I get n1 plus n2 minus 2. But n1 plus n2 is just n. So if I know I've got n vertices total in the graph between the two connected components, I'm going to end up with n minus 2 edges. So a little bit of algebra, a little bit of arithmetic dealing with this theorem that we proved about trees. Again, the theorem applies to trees and not forests. So for general forests, you have to be a little more careful. So here, this leads me to your final quiz of the semester. Quiz CE12 is the following. If G is a forest with 4, why am I writing it as a word? 4 connected components. Connected components. And n vertices. How many edges? You know what I'm going to ask. How many edges does G have? And the argument is very similar to what we just did here. So make sure you understand that. And please feel free to ask me questions if that's not making sense to you. We've reached the end. This is the end of the semester. Thank you so much for bearing with me through all of this, through all the COVID-19 nonsense. I should have said at the outset of this video, in case you didn't make it this far, that you're doing wonderful work. I'm so impressed by how everyone is keeping on top of the homework, the problem sets. I'm starting to get those problem solution videos that you're sending me. Those are starting to trickle in. Excellent work on the second exam. Several of you did exam 2 revisions. Exam 3, some folks are already asking questions about that, even though you got a week or so yet before it's due. A lot of wonderful work being done. Any given semester, this would have sucked. Any semester, it would have sucked to have class all of a sudden abrogated, gone away, and everyone retreat back to your homes. Unprecedented changes in our times. I appreciate how you're rolling with this. This would have sucked in any semester, but it really especially sucked this semester because I was having a wonderful time meeting with you all in class. Despite the fact that it was 8 in the morning, we had great attendance, people were coming, people were engaged, people were really loving working together. You were awake and excited and engaged, and I loved it. And then it ended. It ended sometime mid-March, and it's hard to believe it's been a month and a half since I've seen you all, over a month and a half since I've seen you all and worked with you in person. I appreciate all your efforts. Please, if there's anything between now and the end of the semester that I can do to support you and your work and support your success, reach out to me. I'll keep going on my office hours Wednesday. I'm recording this on Tuesday, the 28th or whatever. So Wednesday the 29th, I'll have office hours from 9 to 10. I'll have office hours next week, Monday and Wednesday as well. I'd like to get everything from you, let's say Friday, May 6th at the very latest. So if you're doing a little makeup work or anything, but please get in what you can. I'm looking forward to hearing from you. Check in with me by email, come to my office hours, anything I can do to support you. Thank you so much. It's been wonderful working with you all, and I'll talk to you soon.